This is John Black, Super Chemist. This is not an instructional video. It is just a vlog showing a video account of some chemistry experiments I have done or am learning about. I do not go over all safety concerns, so if you repeat anything in the video, you do it at your own risk. Half of it's in the pot, say, half of it's in the receiving flask, and we're up to 46 degrees Celsius, so something did get chlorinated. Not much, though. We'll see when we're done here. See the drip weight picked up. It's about 3 seconds. Maybe 4 or 5, I don't know. I'm not timing it. We're at 47 Celsius now, so something is definitely going on here. I'm still at half. It's slowly, steadily climbing up the temperature. Still hit temperature. Well, it stopped distilling. You can see how much is over there. So I jacked up the heat, and you can see how much is in the pot. It's probably 40% still left in the pot, 60% distilled. And when I turn the heat up now, it's jacked up to about 54 degrees. So there's definitely been some chlorination. There's no way that that is distilling at that high. Because the DCM that I used had all been distilled over at 40 degrees Celsius. So coming over at 54 is crazy, unless it was chlorinated. Well, I changed out the flask. It's now at 60 degrees. It's actually 62 degrees, but it's coming over kind of fast, as you can see. 1 Mississippi, 2 Mississippi, 2.5 Mississippis. So 60 degrees about is somewhere around there is the boiling point of chloroform or trichloromethane. So I did make trichloromethane using 0 UV light and only blue light. So the free radical halogenation did work, just didn't work as good as I wanted it to because I did it so fast because of the leaks. Here's what's left in there. You can see not much. There's what's in there. And now this is the stuff that was, it's both DCM and trichloromethane, but mostly DCM. So you can see between this and this, you know, that might be maybe 30%, 40%. We'll see when I'm done. So there was some type of chlorination that happened, that's for sure. Alright, I'm done. There's probably, this is a 25 milliliter flask, so there's probably maybe 5 milliliters in there, if that, of trichloromethane. So it did work slightly. Here's what, now there is some trichloromethane in here too, but mostly it's DCM, dichloromethane. And then the pot just has, you know, like a milliliter in it, milliliter or something like that. You can't even see it. Now this came over between 59 Celsius. I mean, as soon as it hit 57, it was there for, as soon as it hit about 55, 56, 57, it stayed there for a little bit. And then it jacked all the way up past 60, like 61, 62. And so I took the temperature down. Everything that came over was between 58, 59 Celsius and 65 Celsius. So there probably was a little bit of tetrachloromethane in there, but not enough for me to isolate it just with one distillation and one Vigorix column. So say I got 4 or 5 milliliters there and say a milliliter inside this DCM, you know what I mean? So it did work. Not as good as I wanted it to, obviously, but I did make some chloroform. And obviously, because I went too fast and I wasn't boiling it when I did the halogenation, it was too fast. So this first equation is how to make chlorine, calcium hypochlorite, drip some acid on it, a strong acid like HCl, and you'll make chlorine. Now you can see this is the mole of that, and the reason why I divide by 0.68 is because when you buy shock pull cleaner, you know, the rest of this, the 32%, is calcium chloride, and so you have to divide by 0.68 because only 68% of it is calcium hypochlorite. So that's 210 grams. I times everything by 0.75 across the board. So that gives me 157.7 grams of calcium hypochlorite. The HCl is over here. I always just, because the concentrated stuff you get at Lowe's, it's 100 milliliters is actually more than a mole, but I always just say 100 milliliters. Times it by 4 because there's 4 moles. That's 400 milliliters. And like I said, across the board, I'm taking everything by 0.75. So I need 300 milliliters of HCl to drip on 157.7 grams of calcium hypochlorite, or shock. That'll make 2 moles of chlorine. And you'll see the next equation, I'm using 2 moles of chlorine. So this works out perfectly, right? Plus DCM, plus HV, which would be my blue light, 450 to 460 nanometers. Delta T, you want to reflux it, and if everything goes right, you would make tetrachloromethane, right? You would add 2 chlorines onto the DCM to make this, and 2 chlorines onto here. When it plucks off a hydrogen off of there, off of the DCM to add the chlorine, you'll have HCl, right? So 2 moles of this, 71 times 2, 142 grams of chlorine, 64 milliliters per mole of DCM. And remember, I want to times that, multiply everything by 0.75. So that leaves me with 48 milliliters. There's 97 milliliters per mole of tetrachloromethane. I multiply that by 0.75 to get 72.75 milliliters. Now that's what I was hoping to do, make tetrachloromethane. And if I had everything went right, I would have 2 moles of HCl coming out as a gas because it's not soluble in the DCM or trichloromethane or tetrachloromethane. So it's just going to bubble right out of there, right? And I did have a scrubber or a bubbler there, and I put sodium hydroxide in, right? So I can make sodium chloride and water. Now sodium hydroxide, 40 grams is 1 mole. There's 2 moles of HCl, so I'd multiply that by 2. I need at least 80 grams of sodium hydroxide in the scrubber to scrub out this HCl I'm making, okay? There's the boiling points of dichloromethane, trichloromethane, and tetrachloromethane. You can see the boiling point steadily goes up from 40 to 60 to 77. Now that's a good indicator if you have a thermometer in the pot. You know what I mean? It's going to start out at 40 degrees, and the more chlorination you get, the, you know what I mean, the more the temperature will rise. That was my thinking. But after doing the experiment, I think this experiment might be exothermic. It may produce its own heat and raise the temperature and fool you. You know what I mean? But you can also go by volume, okay? The more chlorines you have on there, the more volume you're going to have. And you can mark that on your flask, you know what I mean? So you know if you're getting close or not to your target volume. And another thing I should have done, but I didn't, was weigh the flask beforehand, then weigh how much dichloromethane or DCM I was putting into the pot so that I can weigh it after the experiment. I didn't do that, so I had to distill it to see which, you know, how much chlorination did happen. Now, obviously, if I was trying to make tetrachloromethane, I got a 0% yield. All yields are based on the DCM. That's the limiting reagent. And I would have a 0% yield.
But if I was trying to make trichloromethane, you can see that trichloromethane has a molar mass of, or a molar volume of 80 milliliters, or 79.58 milliliters. I got 6 1/3 milliliters of trichloromethane. Okay, I divide it by its molar mass, and I get 0.07958, and that's approximately 0.08 or 8%. So I did get an 8% yield if I was trying to make trichloromethane based on a limiting reagent, which would be DCM. So 8% is terrible. I should have got 90%, no matter what I was making. But as you'll see from this clip, I'm going to re-show this clip. You'll see how fast I had to do it. I had a leak in the apparatus that I could not find, and the fume hood had a leak also. So the room immediately flooded with chlorine. I can't complain, because it proves one thing: you do not need UV light. Okay, there was zero UV light. I even turned off the incandescent light bulbs so that zero UV would get to the apparatus. And if you needed UV, then I would have zero. I would not, there's no way I could get 8% chlorination if I wasn't creating free radicals with the blue light. Now, here are two reasons why I think that 8% is a great yield, okay? Number one is I couldn't reflux the DCM, okay? This was my apparatus that was getting refluxed, and I'd have chlorine getting bubbled in. There's a tube going in, bubbling it in. Now, I should have refluxed it, right? That means there would be vapor all the way up to this line right here, say, right? But I couldn't do that because I couldn't stay in the room more than a second. And I didn't want to keep the heat on and have, you know, a problem with this over refluxing, you know what I mean? So I just turned off the heat for the refluxing. And so all I had when the chlorine bubbled through, it only had this little bit of space here, right here, this little inch down at the bottom, right, to actually react. Once it bubbled through and came up into the flask and into the condenser, there was no DCM because I wasn't refluxing. So all of this area, this is like 90% of the time or distance that it had to go through that it didn't get to react. You know what I mean? If I had been refluxing, it would have from this distance to this distance. But instead, it only had from this distance to this distance. You can see that's only like 1/10 of the space, 1/10 of the time to react. Another reason, which I already mentioned, was the 46 hours I was going to do the reaction, and I only did it in 15 minutes. Let's say I wanted to do the reaction in 4 hours. I did it in 15 minutes. That's 16 times faster. And if I wanted to take 6 hours and I did it in 15, that's 24 times faster. You know what I mean? 1/24 of it. You know what I mean? That's a big difference. And if I can slow that down and reflux it, just imagine if I got 10% just doing it through this little inch and blasting it through there in 15 minutes, and I got 10% chlorination, or I mean, not 10%, I got 8% chlorination. Obviously, if I slow things down or reflux it, I'm going to get a 90% yield or better, okay? Now, I want you to think down here, I got the math. There's 22.4 liters per mole. That gives me 33.6 liters. That's how much I made in chlorine. And it took me a 1/4 hour to bubble it through. That's 134 liters per hour, or 2.24 liters per minute. That is a lot, okay? That is way too fast, all right? That's a lot of... the next time I do this experiment, I'm definitely going to have to make it a smaller scale. That's about it. Everybody have a great day, and always remember, science is great.